So let's start with something that you're all aware of right now. So the Advection-Dispersion-Reaction equation, where you would have the storage in the aqueous phase. So these are the aqueous phase concentrations and a volumetric water content. If you want to make this for an unsaturated zone, this would be a sorbing phase or a solid phase concentration with a dry bulk density. Then we have the advective term. We have the dispersive term, the different forms, whether you account here for the porosity or not. And then we could have reactions in the aqueous phase, and we can have reactions in the solid phase. So this is kind of the type of equations that we're looking at if we're solving for reactive transport. And those who take the crunch flow course should have seen something like this. And this is, of course, not complete. So you need some law for the mass exchange between the aqueous and solid phases. This could be kinetic or at equilibrium. You need rate laws for the reactions. So that somehow these reactions here depend on concentrations in both the aqueous and the solid phases. You need initial and boundary conditions, and then you need parameters. As one of the problems that we have with these type of systems, the more processes you try to address, the more parameters you have. So one of the questions that we were thinking about intensively is how you can make this simpler without making it too simple. And Jesus will most likely say that whatever I do is too simple. Okay, so if you divide this by the volumetric water content, which we often do, you have here the rate of change of the aqueous concentration, and now you get here different velocity. In my lecture notes, this is called the seepage velocity. Others call it the effective linear velocity. And we love to have it this form, that you have the rate of change of the aqueous phase concentrations without a prefactor. That's essentially all that there is about that. Now, in order to solve this thing, and I'm thinking now in terms of a highly resolved field, it's already Darcy scale, you first have to solve for the flow problem. So you have a 3D vector field of velocities. And that's kind of bad in several ways. So it's 3D, it's spatially variable, and it creates a lot of problems. Okay, so in heterogeneous domains, the velocity will be anything but uniform, and that is causing problems. And one is that the computer times are typically fairly high if you try to solve for this thing in a spatially explicit manner, which would be the most correct way of doing it without doing too much of an upscaling. So we've done the upscaling that we said we trust Darcy's law and we don't look at the bachelor scale within pores that you have heard about. So that we think that the local pore scale dispersion coefficient is good enough for things, but you would like to describe the full distribution of hydraulic conductivity and everything that comes with it. There are lots of issues if you do this with numerical schemes. If you have Eulerian schemes, typical things are either numerical oscillations, which for conservative transport aren't that bad, but in reactive transport this could mean that the true concentration is 0 or slightly above 0, and the oscillations tell you it's negative. And all these rate laws have no meaning whatsoever with negative concentrations, and it's physically impossible. So this is something in reactive transport, if you look at those codes, they're made for stability, that you don't get negative concentrations. The price that you have to pay for that is numerical dispersion. So essentially, you overestimate mixing because of numerical effects unless you have very, very fine grids. So that's a problem that we typically face with Eulerian methods. There are some ways to make it better, but you never fully overcome that. Now, if you do this with particle methods, there are also issues. Okay? So there are people who do that, and then you have to express the rate laws that we all have in terms of concentrations as the probability that particles interact with each other. That is not straightforward. So there are people who have done that, but it's not very simple to do that. And there's another issue that is very well known for these particle methods. Low conductivity zones, you hardly get particles in. If you don't have enough particles in there, it's difficult to get the right statistics for the reactions. And of course, the computational effort to make this good is also very high, so you would need millions of particles, something like this. Okay, so that's kind of the problem. And then there's another dilemma, let's say on a somewhat more philosophical level. You have nonlinear rate laws, okay? You have spatial variability of hydraulic and chemical parameters, where we definitely don't know all the details. You need a fine resolution to overcome numerical problems, as I tried to explain. So you end up with a very high computational effort if you just do one realization. But everything that we have in there is pretty uncertain. So even if you say I take reaction laws and equilibriums from databases, that's fine. There are enough things in there that are uncertain, including concepts, which is even worse. So you're not sure what you should put into your model. So because of the uncertainty, it would be extremely important that you do an uncertainty analysis. And because of the nonlinearity, practically the only things that really work are ensemble-based. So you have to do many, many, many runs and try to somehow cover all the uncertainties that you know of. On the other hand, we just figured out that the computation effort is very high. So you need you have so many parameters, so you need a good uncertainty analysis, but it's so expensive that you hardly can do it. So this is what I would call a dilemma. Okay, so the major objective, what I try to do here is find a way of how to cheat. That's what this is all about. So find a conceptually simplified description of reactive transport that does not cover all the things that you know of, but major controls, and is computationally so efficient that you can run ensemble calculations. So I'm not satisfied if somebody says, oh, take a catchment, describe it as 3 buckets, and all the reactions are first order. Then you can do all the stochastic analysis that you want to do, but you may not have the right controls in there. So you've got to figure out what the right controls are. So the major thing that I want to talk about today is, so how can you get rid of a spatially variable 3D description in the calculation of the nonlinear reactive transport? It does not disappear, but I only want to do linear things with the spatial variability, and the nonlinear things I want to do in a simpler way. So that's the idea behind it, and obviously you can do this only under very specific conditions. Okay, so let's start with extremely gross simplifications. Steady state flow, so it depends on the scale and your problem, whether this is a good idea or not. Then something that some people find extremely shocking, neglect dispersion. Okay, so, well, there are cases where you can do this. So either the compounds are already mixed. So this would be a typical bank filtration type of problem. So you already have the reacting compounds together, and they haven't reacted because there were no bugs around. Or they mixed due to the exchange with the solid phase. Okay, then the dispersion is not that important that the compounds get together. And diffuse inputs would also help a lot, so not a point source. Uniform initial conditions, uniform reaction parameters, and spatially uniform concentrations in the inflow. So this is what I would call a diffuse input. So it's more something about what's happening, what is the effect when a farmer is applying something on the entire field rather than an individual gas station, as an example. Okay, this is a favorite case of mine that definitely does not work. We'll talk about that in the other talk. So here you would have a source zone that needs to react with oxygen or nitrate, is readily consumed. You create a plume, and the only way how you get oxygen into the plume is by transverse dispersion. So this thing is controlled by transverse dispersion, also on the macro scale, and I just said I want to neglect that. So this case cannot be covered. And there would be other cases that cannot be covered because there are too many dynamics and too many feedbacks. Okay, so let's go back to this equation here. So we have our transport equation expressed in this form with the seepage velocity. And now we introduce the travel time. And I do this in a way that most of you will not find very intuitive. You would think, oh yeah, you do particle tracking, and that's a way how you can compute this very easily. But you can also write this in an Eulerian way. So the advective travel time obeys this differential equation. Yes?
I have a question. What does the S stand for again? Like
This is a concentration in the solid phase of compound I. And it might be a sorbing compound. I just have it for completeness, that you would have also something in solid phases. And you might have immobile compounds, then this here would disappear because they're not transported. Okay? So you can write the advective travel time, it meets this equation here, so the velocity times the gradient of the advective travel time equals 1. So this is an Eulerian way to look at it. In reality, most people calculate this with the particle tracker. Okay, so now we apply little rules of a chain rule of differentiation. So the concentration gradient, we can say, is the gradient of the travel time times the derivative of the concentration with respect to the travel time. This is chain rule of differentiation. And we have here a scalar product with the velocity. Okay, so this remains here. Wait a minute, the scalar product of the velocity with the gradient of the advective travel time is 1. So this thing here becomes the rate of, so the derivative of the concentration with respect to the advective travel time. Okay, so now our transport equation, this here is the same, this is here all the same. I've taken out the dispersion and I have here a derivative with respect to travel time rather than something 3D spatially variable. That's the entire trick, and you can do this in this nice form only, of course, if it's purely advective. And at steady state, if it's not at steady state, you can also do this, but it's more complicated. Okay, so what have we gained at this point? So we had 3 spatial coordinates and they are replaced by 1 travel time coordinate. Oh, that's good. So that's 1D is easier than 3D. Also, we had a variable velocity, and this is replaced by a constant factor of 1. And there can be nothing simpler than that. A constant velocity of 1 if you go into these funny coordinates. Now, in order to get these funny coordinates, you have to solve a 3D transport problem, but not for the reactive case. That's the entire idea behind this. Now, this doesn't mean that everything is fine, because you still have here the reaction terms. Okay? And the reaction terms, do they depend only on travel time, or do they still depend on space? And that depends very much on the type of system that you're looking at. So if you have a system where there are reactions with something in the mineral phase, and let's say it's reacting with the calcite, but it's not reacting with the granite. So if limestone and granite fractured systems, then sorry, it doesn't make a difference if you're interested in, let's say, carbon, whether you're now in the granite or you're now in the limestone. So that would be still a spatially explicit problem. You could still do this thing, but you would have to track many streamlines, and people have done that. Martin Blunt has done these type of things. You would track individual streamlines, and along the streamline you would have to look what type of material do I have. Okay, so that would be still much more efficient than doing the 3D thing, provided that you have steady state flow and you can neglect dispersion. Okay? But there are also cases, at least mentally we can think of them, well, the materials are not really changing that much. In that case, you do have maybe different bacteria at different places, but the reason why there are different bacteria is because everything that is there had undergone the reactive transport further upstream. So this is something self-organizing. And the outcome is that essentially these concentrations here that make up the reactions, they depend on exactly the same operator that you have over there. And independent of where you are in the domain, if you have the same travel time, you have the same concentrations, and therefore the same reaction rates. So it becomes really a 1D problem where you can solve everything along one streamline and map everything from there. So that's the idea. Of course, this only works under very specific conditions, as I said. So this is what I would call self-organization, and I'm going to show you that for certain cases that we, of course, made up that it works, you're allowed to do that. Now, you compute everything in a 1D travel time domain, and then you map the results to the spatial domain. So the concentrations at space and time is the concentration at the advective travel time that we figure out at that location, but that's not a reactive transport problem to get this relationship and time. Okay. So you can call the advective travel time also kinematic H. So these are examples here. for fields that don't look like geology. So these are multi-Gaussian fields. So this is not geology. It's just to create some spatial variability. And what you see nicely is the higher the variance is here, the wilder it gets. And you get very narrow features here. So let's say this guy here it starts to get, you see old water. And the reason is that here is a little zone of low hydraulic conductivity. You have low velocity. And everything that is downstream is old. Because there's no way that something mixes in from the side. That's advection. Okay? And it's getting wilder if you have higher variances. Okay, so now let's look, before I do any real reaction, so what is local dispersion doing? Local dispersion means the smallest Darcy scale that you're allowed to take. So it still assumes steady state flow, uniform initial and inflow concentrations, uniform chemical parameters. So there's still very gross simplifications here. So let's look here at, this is a picture of the advective travel time, how this might look like here in one of those cases that I've taken. Let's first look what does local longitudinal dispersion do. So this would be the operator in the longitudinal direction, and I have here now the longitudinal spatial coordinate. So I go into orient myself in streamlined coordinates, you might say, and this is the longitudinal dispersion coefficient. And of course, I can make now a very easy change. I can go from the longitudinal coordinate to the travel time by scaling everything with 1 over the absolute value of the velocity. If you look this thing here up, you might say, well, okay, I can come up quite easily here with a diffusion coefficient or dispersion coefficient and travel time coordinates that has funny units because you have divided it twice by the velocity. So this has now units of a time, okay, so that it works out. And of course, we know that along the individual streamlines and individual points, this will not always be the same value, but at least structurally, we are not introducing too much of an error if we come up with, let's say, a simple law of how to estimate this thing here, and we would be doing fine. Actually, this is the boring case. So the more interesting case is always the transverse. So this would be here an exchange that is perpendicular to the direction of flow. Okay. Now we're in a framework where everything is about old or young water, and that means you're still mixing old and young water. So we say everything is introduced here uniformly. Some of it is moving ahead more quickly, some of them is moving ahead more slowly, and you have an exchange between the streamlines, and this is an exchange of old and young water in some way. And so you might try to parameterize the effects that you have here that on the long run are much more relevant than the local longitudinal one by the same law. So this is now some kind of an effective longitudinal diffusion coefficient expressed in these funny travel times.
Well,
yes?
Well, is that really a label on the vertical axis? It looks like you're labeling a vertical axis, but then I interpret the color bar as...
No, this is wrong. This should be here something else. Yeah, this comes here, oh, there were other plots. And this was the plot for the advective travel time, and there was another one for another one. So forget this. This is a Y or a Z or whatever you want.
Space.
Yeah, the space. So, yeah.
If it's not too much to ask, can you talk here?
I can talk on all sides that you want. I can also talk from the back. Okay, so this is a parameterization. This is not true.
Absolutely not true.
Well, wait, we're going to see that. So I'm going to show you where we introduce errors. Okay, so there are places where there's really very young water adjacent to very old water, and there you would need a different coefficient than at places where it's only smoothly varying. Okay, so but what we'll see that actually, if you come up with a nice law of how to do this here, you don't introduce too much of an error. Okay, so what would be the right coefficient here? Okay.
So before going
Yes.
just like
Yeah.
go back to the funny units
Yes.
again. There's like the funny
Yes.
units for,
Yeah.
like the previous one.
Yeah, that's the same thing here. It has the same units.
So that one you can have units of
This has a unit of a time.
time.
Because it's a dispersion coefficient which has meters squared per second divided by the velocity and divided again by the velocity. You factor this in here kind of as an effective law. So you take meter squared per second and you multiply it with seconds squared divided by meter squared, so you end up with seconds, which is kind of funny. But if you go into the governing equation, you need rate of change of concentration, and you have a thing like this here. So this is a time, this is a time, this is a concentration. So you want to have a concentration over a time, and you have a concentration divided 2 times by this got to have a unit of a time. And you get this by scaling it with, inversely scaling it with the, or scaling it with the velocity squared. Okay, but that is a local type of thinking. In reality, you have to do it slightly differently. Okay. So one thing is, upon mixing, the groundwater H that you have is not an individual value anymore. It's in reality a distribution. So if you, I tried to come up with the numbers this morning. So you really do a point measurement in a single aquifer. And let's say you take 1 nanomole of water. So that's 1 nanogram of water. This is really very, very tiny. Okay, so you could say this is what, let's say, a bacterium is seeing. Okay, these are still 6 times 10 to the power of 14 molecules. And if they all had a little watch, which they can't, so, and you could ask them, how long have you been in the system? Then in this 1 nanomole of water, some of them would say, well, I've been here 10 days, and the others would say, I've been 12 days, and others 9 days. So it will be a distribution.
10 years.
Or 10, well, one of them will say 10 years, or maybe even 1,000. Okay, so this is a full distribution because of dispersive mixing. Okay? So you don't have a unique value anymore. That's very well known. However, you can compute very easily, and this is very old stuff, the mean groundwater H and the variance of the groundwater H. The mean this is the mean groundwater H equation. So this comes from Gude and Konnikov. So it looks like before, but we have here now this operator of the dispersion. Okay, so this is doing something. And the variance, you have something that you have seen before. So like this scalar dissipation rate, you have the same thing. You take the gradient of the mean travel time, a quadratic product with a local dispersion coefficient. So you resolve the dispersion, the velocity field. So this is really a 3D thing. So this is something that comes out kind of naturally if you go through moment generating equations. So you can compute this if you want to. But of course, that doesn't help you if you want to come up with a simple law. So now you would have a very funny distribution. And you see this here. So this would be a log K field. This would be the mean groundwater H. And now this is where this came from, why John was a little bit confused. So this is only the advective groundwater H, the kinematic H. And you see you lose here features. So all these fine scale features, they're gone because of transverse mixing. And the mean groundwater H, and here is the computed variance. And this, in a way, looks awful. Okay? However, in average, you can figure out there is kind of a relationship between this pattern and that pattern. Okay? I mean, it's not a one-to-one relationship. Not at all. Okay? But if you want to parameterize it, if you want to upscale it, you will say, okay, so let's see, what do we find here a relationship between those two here? And how would this happen in a homogeneous medium? Okay. So now everything is now in travel time coordinates, and I work now with this mean groundwater H as my proxy for space. So it's still a 1D model. All mixing is between young and old water, and you can argue whether or not this is a good idea or not, or you need a different parameterization. But whatever your parameterization is, it will not resolve that in reality you have spatial variability. This is lost to a large extent. Now you definitely need a spatially uniform inflow concentration, because you would now also mix water that is not only old and young but of different origin. So if you have different chemical signature, this is creating problems. Now, in this parameterization, this effective diffusion coefficient is allowed to vary with the mean groundwater H, but the way it's written, it's only allowed to vary with that, because we don't have any other coordinate. And the way how we've done it, that's where we said, okay, we look at the dependence, so we compute this thing here, and we look at the dependence of the variance of local travel time distributions and the mean, and we actually used a linear law or something like this. We just fitted it, but you could do this better. Marco could give you equations how to do this better. Okay, so now let's see how bad we're doing, and the example that I'm using all the time is denitrification. And this is coupled to aerobic degradation, and the problem is here of bank filtration, so river water infiltration. Oxygen and nitrate are the electron acceptors. Dissolved organic carbon is the electron donor. All of that is already in the river. Elevated oxygen concentrations inhibit the denitrification, so this makes this thing definitely non-linear. The reactants are already mixed in the river, and then they're jointly transported into the riverbed and do their things there. We also consider immobile microbes. This is a typical assumption that we love to do. Both aerobic and denitrifying bugs, they're growing upon the reactions. And then there's a miracle thingy that people love to do in these type of models. It's called the carrying capacity. So the biomass cannot exceed a maximum value. And there's a big debate where this is coming from, but it is an observation. Okay, so typically it's something fitted. Okay, if you look at the stoichiometry of the reactions, for the denitrification, you would have your one, the DOC is always CH2O. So one DOC with 4/5 of nitrate, but there is a little bit reduction of what goes into the biomass, so reacting to nitrogen, and this is what goes into the biomass, and I always measure the biomass in carbon to make stoichiometries easy, so carbon in the biomass. For aerobic metabolism, you would have a 1:1:1 if there was no growth of the biomass, but a certain fraction of the carbon is used to build biomass. And you can actually think which fraction this is and what determines that, but that's not the topic here. So this fraction that goes into the biomass is called the specific yield. The biomass concentrations are measured in carbon per water. And we made in this model two different types, but there are also bacteria that can do both, and there are all kinds of things. And then the classical law to express rate laws is the double monokinetics. So this term here is expressing the dependence on the DOC. So if the concentration is much higher than this Monod coefficient or Michaelis-Menten coefficient, this thing here goes to 1. Okay, because this is much smaller, this is much bigger than that, so this goes to 1. If it's much smaller than this Michaelis-Menten coefficient, then this here is much smaller than that, it becomes a first order law. You do this with the DOC. You have something inverse for the oxygen to get the inhibition. And then here we have the maximum specific growth rate, number of bacteria, the yield. For oxygen, we have something similar, but we don't have this inhibition in there. Okay, so this is the 1D model, a 1D invasion. It's a little bit difficult to read. So this is time. This is travel time, or you could say a 1D column. And there's a normalized concentration. So all concentration goes from 0 to 1. And for the tracer, we use the negative tracer that you see something. So it's kind of boring. This is just simply replaced here. Okay? So over time, it moves out of the system. Now, it's very artificial. So there was practically nothing in there. And then oxygen, DOC, and nitrate together penetrate the system. There are hardly any bugs in there. So first they behave like the conservative tracer. The DOC and the oxygen, this leads to a growth of the aerobic bacteria, and that leads to a strong reduction of the oxygen after a certain period of time. So after a certain period of time, you don't see any oxygen further downstream anymore. And you see less of DOC. This is this little edge here. Okay? And once there is no more oxygen, the nitrate can be consumed, and the denitrifying bacteria see, oh, I have DOC, I have nitrate, I can grow. There are practically no denitrifiers here in the background, and then they always grow up more or less to this maximum biomass concentration. And of course, with MATLAB, you can do wonderful, colorful, shiny pictures. Okay. So now let's look at how does this look in this 2D heterogeneous domain. So the reference case would be spatially explicit. everything in there. And we use streamline-oriented grids. And we tested several mapping approaches from travel time domain to the spatial domain, neglecting dispersion altogether. This is the simplest that you can do. Considering the local longitudinal dispersion coefficient at the average velocity, this is, I can tell you, it's too small. And considering an effective longitudinal dispersion coefficient that increases linearly with the mean travel time that was fitted. And you could do better than that. Okay, so this here is essentially the truth, or the virtual truth, so the model truth, the 2D virtual model truth. After 3 days and after 30 days, this is the nitrate. Actually, what you see after 3 days, the stuff has penetrated into the domain. And after 30 days, it looks as if it has retreated. But in reality, it's eaten up here. Okay, it's like glaciers don't retreat. They're melting away. So here the melting away is that the nitrate is eaten up by denitrifying bacteria, and you see here this funny feature here. So this is essentially where you have a little nozzle, a little trunk of old water, you might be saying. Okay, these are errors. So these are not the same, because if you look at the plots, they look so similar. So these are errors in some normalized fashion for the case of neglecting dispersion altogether, taking a constant value coming from the local value and doing this funny linear trend. And this is at early times. And at early times you see, 15% error. Not so good. Okay? If I use a small coefficient coming from local behavior, it's still a big error. If I use this linear trend, yes, I do something wrong here, but it's not that bad. Okay? After 30 days, actually, everything stabilizes. You don't have this invading front anymore. And even this lousy model where you neglect dispersion altogether is only 5% error. Considering how much errors you have, uncertainty you have, and all the other stuff, that's not that bad. Okay? And this one is actually not doing much better. And if you ask yourself, where is the error? Well, it's along this feature here. Okay? So where very old and very young water are adjacent to each other. Same thing with aerobic bacteria. There you hardly see any change after 3 days or 30 days because these bugs are growing so quickly. And again, you will have higher errors at the invading front if you do something wrong with the mixing. And after 30 days, okay, these absolute values are bigger. But yeah, so there are certain features where you have difficulties. Okay, so we have then modified this a little bit. Said, well, do the same thing, joint injection of substrate, oxygen, nitrate. Now we have diurnal fluctuations of the velocity, but only in its magnitude, not in its direction. If you change the direction, none of that works. Okay? So essentially it's pumping water in and out. This could be something like hydro-peaking or so for bank filtration. And again, a spatially explicit model as a comparison. So this is the spatially explicit model. After a certain time, it all stabilized. And you see how this is pumping back and forth. And these funny lines here are isochrones, so lines of identical travel time for the average velocity. And actually, the nitrate here is always moving to this fat line here. It loves the fat line. And then it retreats again because you have high velocity, low velocity. But actually, with these lines here, you can explain most of the patterns. And for the aerobic bacteria, they more or less stay put. Okay, so these are 2D results, mapped 1D results, and differences. Let's have a look. At the end of the simulation, it's very difficult to see any difference here. I would say if you look at the difference, yes, you see there something is wrong here. But altogether, it's not doing that badly. Okay, so you can explain most of the spatial variability for this very specific setup. I'm not saying that this is good for everything. So lessons learned at this point. So travel time-based simulations of reactive transport are good approximations if macroscopic transverse mixing is not decisive. So something where you have a plume and you have to get something in from the sides does not work. Not at all. But it's a macroscopic perspective because microscopically it's always the transverse that is doing the job. even if it's a macroscopically longitudinal mixing. Chemical parameters are spatially uniform. Direction of flow, the direction of flow does not vary in time. Effective longitudinal mixing needs to be parameterized at least at an invading front, okay? But it's less important at late times for this type of setup. Okay. Now, this thing here is shaky. Okay. So this one here, we don't like. Okay, so let's see what, we have now a slightly different story. So fate of nitrogen-controlled electron donor, it's now released from the matrix. And we're looking into these things currently. So very similar as before, but now we say that the DOC is somehow released from the matrix. Okay? There's natural organic matter. This is called NOM here. So, and that is releasing this with some first order law. And you might say this is not correct, but it's very difficult to get this type of information from biogeochemists. And then we say, well, this is not happening everywhere. So there are zones where you have lots of natural organic matter, and there are zones where there's little. Let's say peat lenses. Okay? There you have lots of it, and then in a sand you don't have that at all. So this will at first lead to a binary chemical heterogeneity. Let's have a look here. This would be NOM, NON, NON, going towards a river here. And now we have here a water droplet, oxygen and nitrate. It goes through the first zone here. Whoops, all the oxygen is gone. And then nothing happens. And then, or a little, when we say in this case nothing. And then you have some decrease of nitrate. Nothing happens. A little bit more decrease of nitrate. And whoops, we're out in the well. Okay, so that's the type of thinking. Okay, so the way how we addressed this was, well, we haven't invented that. So this is all old. But this is a lecture. I'm allowed to tell you old stories. Because you can do this with what we call exposure time. And the exposure time would be the time that the water parcel has spent in the reactive zone. Okay? So essentially you say the time doesn't matter if it's a non-reactive zone, if you're in the quartz sand. Okay? So that's why there we have a source zone of 0, and otherwise we're a source term of 1. And then we use more or less the same type of mapping approaches, but with exposure rather than travel time, and you have to think about what you're doing in these non-reactive zones. I don't go into any of those details. I call this here the cow pattern problem. So this is a Holstein cow. So the reactive zones are black, and the reactive zones have low hydraulic conductivity, and the white zones is non-reactive. Flow net, travel time. The exposure time has a slightly different pattern. Okay, wherever it's white, it does not increase, and that would be different between those. And in the low conductive zones, we have the high release of DOC, and in the high conductive zone, no release of DOC. So this is a comparison again between a full calculation and exposure time-based model. Substrate, and this is a residuals here. So this is the DOC. Well, not that bad. Okay, oxygen. You see again here some features. So these elongated features that can have some problems somewhere here, somewhere there. The nitrate, but overall the patterns don't look that bad. Here you see something funny going on. Here it looks differently. What's really awful are the bacteria, because our model does not, we have no clue what to do with the bacteria in the non-reactive zone, so we said they have to be 0. And in reality, there can be some stuff washed in from the upstream side. Okay, so the biomass in the non-reactive zones is maybe not that good. So that was good, but in a way, so we wanted to make it even simpler, and we wanted to extend it at the same time. Okay, so one observation is that the buildup of biomass actually takes for aerobic bacteria days, and for denitrifying bacteria maybe weeks. And typically, if we're talking about these type of problems, we're interested in years. So you might say, come on, I'm not interested what the bugs are doing in a virtual setup where there was no oxygen at all, and all of a sudden there is oxygen, and now they need 3 days to grow. That's kind of not a real problem that you could face outside there. So this is rather quick. Yes. So the microbes actually grow until the local steady state of DOC release and consumption. And often this is close in this calculations to what we call the carrying capacity. There's something that I want to talk in the other talk, that the microbes actually can cope with transient conditions fairly well. They can go to sleep. And another mechanism that's actually good is biomass transport. So there's a permanent inoculation by cells. So that is actually good. So actually, we said we don't consider the microbes at all. We just say they're there. They're doing all the job, but we don't care how they do it. They're there. They're doing the job. Now, with the exception of the invading fronts, dispersion is not needed. That was what I said before, so I also take this out. But the extension is that we say the reactivity cannot be binary. It could be a high reactivity or low reactivity. And we call this a relative reactivity. This is a concept. Whether it's good or not, we are not 100% sure yet. So this is, we call this small f here. And essentially the idea is the following. So the release of the electron donor from the matrix is addressed as a reactivity relative to a reactivity under reference conditions. So I have here a reaction rate for given concentrations. Okay, and I multiply this with a scalar field. So these are my type of rate laws. There's no more biomass in there. There's no DOC in there. Instead, I have this little F field here, and that can vary in space. Okay, a few mathematical tricks. Advection-Reaction equation with a variable relative reactivity, now in red. Isn't that cool? You can take the material derivative along a trajectory. Okay, well, you still have this thing in here. And now we make a little trick. We take the integral of this relative reactivity along the path line. And this is the cumulative relative reactivity. Okay? And then the reactive transfer along the trajectory becomes, wow, this is a single differential equation where I have replaced time with this funny cumulative relative reactivity. So all the reactions are solved by solving one ODE system. Okay, single ODE system for one initial set of initial concentrations. That's the idea. And it's still nonlinear. Okay, so the relative reactivity is asking the question, how strong is the electron donor source in comparison to reference conditions? And it depends on the type and amount of the electron donor source in the matrix. And the cumulative relative reactivity asks the question, so how much of that has a water parcel seen on its way to an observation point? Okay. And actually it has units of a time, and you could imagine this. So the water parcel has a little clock with it, and when it's in a high reactive zone, the clock goes tick, tick, tick. And if it goes through a low reactive zone, it goes about tick, 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 tick. And then you look up 12 hours of cumulative relative reactivity, or whatever. Okay, so that's the idea. And you can evaluate this easily by particle tracking. Okay, and that's actually how we've done it, and we've done it with on the graphics card. So this is like this, and it's a completely linear problem. So you can imagine this essentially an aging of a water parcel so this is causing a decrease of oxygen and nitrate. So first the oxygen is gone, and then when the oxygen is gone, essentially the nitrate starts to decrease, and we try to come up with simplified laws that we actually even have closed form expressions for that. Okay. So a little proof of concept application, 1.5 million cells, groundwater recharge contains nitrogen and oxygen. We used MATLAB, ModFlow for flow, particle tracking MATLAB on the graphics card, but MATLAB can do this very efficiently for you. You don't need to know anything about GPU programming. And it took 12 minutes to do this, and most of that because ModFlow is so slow. Okay. So here you would see hydraulic heads of half of the domain. There is a little well here. This is the reactive zone. Within, we introduce some distribution of this relative reactivity. And by doing backward tracking from all the 1.5 million points, you can map out the travel times and cumulative reactivity everywhere. So it does not get larger behind this zone here. The rest is mapping. So we solve this one ODE system per inflow concentration set. We have this thing, map it, and get plots of nitrate and oxygen. And you could do this also as a time variant problem of what is actually entering the aquifer. Not talking about the root zone where there are lots of funny feedbacks. So we would be looking at what is leaving below the root zone. So there, all of this would, in the soil, it would not work. Okay, so the last thing that we did, then we talked, there was a wonderful paper, and one of the reviewers said it's very elegant. And then everybody who came from geology said, wait a minute, you're doing something completely wrong here. You're consuming stuff that is coming out of the matrix. So after a while, this will be gone. You have to account for that. Okay, so actually you have your stoichiometry, 1 oxygen, 1 organic carbon, or 1 nitrate and 1.25 organic carbon. So you deplete this source. So if you want to account for that, you need a functional dependence of this funny relative reactivity of how much carbon you have in there. Very difficult. So I'm very shaky what we did there. And then, of course, if you consume these natural organic matter, then you have less cumulative relative reactivity, so you have to update this in some way. And it becomes a spatially explicit problem again, because you have different consumptions at different places, but you can still do this along travel times that are discretized in travel time increments. So that still might work. We had here a little, now it's only 750,000 cells, again with mod flow. This is hydraulic conductivity, 2 different layers. We've cut something out here. Organic carbon content, there is some anti-correlation, the relative reactivity that comes from that. Here is a river that is infiltrating. There are pumping wells and observation wells. So the pumping wells actively pump, and the observation wells, we take an average over depth. And we also look at what is happening here at this constant head outflow boundary. And now we actually did what we wanted to do, ensemble calculations. Okay, so these are now percentiles, and these are observation wells. And actually it's horrible. So from one realization to the other, you can see oxygen is gone very quickly, or is arriving very quickly, or you never see this. So point observations are bad in a spatially variable domain because you don't integrate. A pumping well, you start to integrate. You get some bounds here. I mean, there's only spatial variability. And the outflow is integrating over something bigger. So the bigger you integrate, the less uncertainty you have due to spatial variability. I mean, this is nothing new, okay? But we can give you some uncertainty bounds. If you're interested in an individual point, well, forget it, okay? But if you're interested in some integral information, it might work out. And this took 4,000 minutes CPU time on a normal computer. So this is something like 3 days. Of course, the coding took 3 months, but as always, so you can actually do these type of things. Okay, so carry home messages. Travel time-based approaches conceptually simplify reactive transport simulations. It is not the golden bullet for all setups. I don't want to say that you should do this everywhere. Not at all, okay? But it might be suitable under specific conditions, okay? Now, something more general, a model does not need to include all processes and properties that you know of. Here you hear lots of things that are around, and you have to filter this out for your applications. What of all the cool stuff that you've heard is actually relevant for the problem that you're solving right now, and what are things that you might store in your mind and take it out again if you have a different problem? So you have to include those processes that really control the system. So you got to try to figure this out. If chosen wisely, you can then reduce the computational effort dramatically because you don't spend a lot of time on things that are not relevant. But it's sometimes difficult. If you have initially said it's not relevant, then it's of course not in your problem. So that's kind of a chicken-egg problem. A couple of practical challenges. If you want to use travel times in practice, people often use so-called age tracers. Don't believe the numbers that they give you. Okay, so whatever they give you an age, but often in reality they have measured a tritium-helium ratio and they don't see the old component, or they give you some estimate coming from CFCs or a couple of different techniques. And in reality, this is not a fixed number. It would be better to look at the real concentration. Another thing, and I'm done then, chemical heterogeneity exists, we know it, but it's not that well assessed if you compare this to physical heterogeneity. That's my personal impression. And I would like to have something like a catalog of geological structures. So saying, okay, if you're in this type of geological environment, these are the type of facies that you should expect. How large are these guys? What type of hydraulic parameters should you expect? What of reactive parameters, spatial arrangements, something like this. But not only physical parameters, also things like organic carbon content or pyrite or maybe goethite coatings. And then, of course, we have big problems to relate what of the natural organic matter is actually reactive and to which extent biogeochemists could give